The universe is a living ocean of energy, motion, and silence, a place where every second becomes a page in an endless chronicle written in starlight. Tonight, our story begins with a question that seems simple yet opens the gates to infinity. How much do we truly understand about the invisible forces shaping our cosmic neighborhood? This video is about three breathtaking events that shook the world of astronomy in recent months. Mysterious flashes in the sky, a visitor from the interstellar void, and a discovery that changes our understanding of how the darkest hearts of galaxies evolve. Together, they form a picture so grand that it feels as if space itself whispered it to those who dared to listen. Let us begin with a moment of wonder. Late in October, as dawn was still resting behind the horizon, a bright object streaked across the Moscow sky. Dozens of cameras caught the trail of fire tearing through the morning air. It burned white and golden, brighter than Venus, perhaps even brighter than the moon itself. What was it? A piece of an old satellite returning home after decades of wandering? Or something more ancient? A fragment of cosmic stone, cold and lonely, born long before our sun ignited. Astronomers call such bright travelers bolides, meteors, whose brilliance rivals the brightest celestial bodies. And each time they appear, they remind us that the Earth is never alone. Around us, hidden in the darkness, countless objects drift. Fragments of history, messengers from forgotten worlds. The mystery deepened as experts examined the footage. Some said it was space debris, others were convinced it was a natural body, a meteor that had survived the icy vastness between planets. The truth remained uncertain, yet the very uncertainty became a story of its own. Because behind every falling star lies a silent dialogue between humanity and the cosmos, a question asked in light, an answer burned into the atmosphere. And while that question still hovered over Moscow, another was being asked far beyond our skies. Astronomers across the world turned their telescopes toward an unusual wanderer, the interstellar object Triatlas, officially named Three-Eye Atlas. It came from beyond the boundaries of the solar system, moving along a trajectory no comet from our neighborhood could ever follow. Its glow was strange, its structure unique, and as it approached the inner planets, it revealed something never seen before. An anti-tail, a luminous stream pointing not away from the sun but toward it. The discovery stunned even experienced astrophysicists. Was this a new type of interstellar matter? A natural phenomenon never recorded before? Or could it be, as some dared to whisper, evidence of something created? A vessel, perhaps, built by hands we have never seen. We had only begun to understand what Triatlas truly was when yet another revelation reached Earth, a story that began not with light, but with the tremor of space-time itself. The world's gravitational wave observatories in the United States, Europe, and Japan captured something unprecedented, the merging of black holes not born as ordinary stellar remnants, but as children of earlier black holes. A new generation, a lineage of darkness within darkness. Scientists called them second-generation black holes, a phrase that echoes with both awe and unease. What kind of universe breeds such monsters, and what stories of cosmic creation do they carry in their silence? These three events, the Moscow bolide, the interstellar visitor, and the awakening of new black holes, are threads in a single cosmic tapestry. Each points to a future where our instruments no longer merely observe but listen, where light and gravity together tell the story of the universe's hidden architecture. Tonight, we will unfold that story, how scientists unraveled each of these mysteries, what they found, and what it tells us about our place among the stars. But first, take a moment to imagine. You are standing under the night sky. The air is cold, the city sleeps, and above you something glows, a traveler from the depths of space, burning its final breath before vanishing forever. You look up, and for a second, You feel the heartbeat of the cosmos. What if that heartbeat is trying to speak? What if every flash, every pulse of light, every trembling wave across the fabric of space is a message? Perhaps tonight we will learn to listen. It began with a flash that cut through the stillness of dawn, a luminous tear across the fabric of the Moscow sky. On the 27th of October, just before sunrise, dozens of early risers witnessed what at first seemed like a falling star, but soon revealed itself to be something far more dramatic. The light was so bright that it turned the rooftops pale and painted moving shadows on sleeping buildings. In seconds, it vanished, leaving behind questions that rippled through the world of astronomy. Was this a messenger from beyond the solar system, a forgotten fragment of a comet's heart, or the charred remains of humanity's own machines returning home after decades in orbit? Scientists immediately began to analyze the countless amateur videos that poured onto the internet. Astronomers, meteor specialists, and astrophysicists traced its motion, its brightness curve, and even the direction of its flight across the firmament. At first, it seemed obvious that this was space debris, perhaps a fragment of a defunct satellite or an exhausted rocket stage, entering the atmosphere along a shallow trajectory. Its flight path, moving gently along the curvature of the Earth, rather than plunging steeply downward, supported that idea. Objects like these, made of metal and fuel tanks, often break apart slowly, scattering fragments that glow for several seconds before fading into smoke. But then came the counter-arguments. More videos emerged from various regions, from the Moscow suburbs, from northern towns, even from distant villages. By carefully comparing the star backgrounds visible on the recordings, experienced observers realized that the object's path was not from west to east, as it would be for most artificial satellites, but from east to west, the opposite of nearly every orbit designed by human engineers. This reversal changed everything. Only a handful of nations ever launched spacecraft in such a direction, and none were scheduled for that morning. The hypothesis of space debris began to fade, replaced by a more fascinating one. The bolide might have been a natural body, a genuine meteorite entering Earth's atmosphere at astonishing speed. The difference between the two possibilities lay in velocity. Artificial objects orbit at roughly 8 kilometers per second. Natural meteoroids, drawn in by Earth's gravity, can strike the atmosphere at speeds exceeding 70 kilometers per second. Observers noted that the Moscow bolide seemed to move faster than any typical piece of debris. If its true velocity exceeded even 15 kilometers per second, then it could not have been man-made. It must have been a fragment of cosmic rock, a survivor of billions of years drifting between worlds. That realization lit a spark of excitement among astronomers and meteorite hunters. Where might the remnants have fallen? Some calculated that, if it had survived its fiery descent, its fragments could lie somewhere in the forests of the Vologda or Novgorod regions, vast, sparsely populated lands of rivers, lakes, and ancient soil. Expeditions were proposed, equipped with metal detectors and mapping drones. For scientists, even a pebble from such an event could reveal priceless data about the composition of small bodies that orbit between planets, or perhaps wander through the solar system from more distant origins. While eyes and minds on Earth searched for answers to this celestial visitor, telescopes on the opposite side of the planet were fixed upon another traveler, one far older, colder, and stranger. It was catalogued as 3I Atlas, or Triatlas, the third confirmed interstellar object to pass through our solar system. Unlike asteroids and comets born alongside our Sun, this one came from the deep galactic void, perhaps ejected from another star system eons ago. Discovered by the automated Atlas telescope in Chile, it appeared at first to be a faint, slow-moving dot among millions of others. But as its orbit was calculated, scientists realized its path was hyperbolic. Not elliptical, like that of a bound comet, but open, meaning it would never return. Then came the first surprise. As Triatlas approached the inner solar system, astronomers detected a peculiar structure surrounding it, a soft haze of gas and dust stretching toward the sun rather than away from it. Comets typically form tails pushed outward by solar radiation and the charged particles of the solar wind. Yet this object seemed to defy the laws that govern every known comet. An anti-tail, they called it. A luminous spike pointing sunward, an apparent rebellion against the very forces of physics. At first, speculation ran wild. Could it be artificial? Some researchers, including the Harvard astrophysicist Avi Loeb, known for his bold interpretations, suggested that such anomalies might indicate technological origin, perhaps debris from an alien probe, or even an object deliberately sent to explore planetary systems like ours. But careful analysis, grounded in spectral data and physical modeling, soon revealed a more elegant explanation, one that, while natural, was no less extraordinary. Triatlas, it turned out, contained an unusually high proportion of frozen carbon dioxide, dry ice, far exceeding the amount of water ice usually found in comets of our own solar system. This composition suggested it was born in an extremely cold region of space, far from any warm star, where carbon dioxide condenses more easily than water. As the object drifted inward toward the sun, the carbon dioxide began to sublimate first, turning directly from solid to gas and dragging with it clouds of icy dust particles. Because the nucleus of Triatlas rotated slowly, one full spin every 16 hours, only one side was heated for long periods, causing gas to escape persistently in a single direction, toward the sun itself. That focused outflow created the illusion of a tail pointing the wrong way, the now famous anti-tail. The phenomenon captivated the scientific community. Telescopes from Hawaii to the Canary Islands joined in observing the visitor. Spectrographs recorded the signatures of carbon dioxide, methane, and faint traces of complex organics, possible building blocks of life, frozen in darkness for billions of years. Each photon reflected from Triatlas carried with it a whisper of a distant stellar nursery, perhaps hundreds of light years away, where another sun once burned, where another system of planets once circled. The object had traveled across the galactic disk for ages, wandering through the cold emptiness until gravity guided it, by chance or by destiny, into our neighborhood. And as this ancient voyager approached its closest point to the sun, another discovery, quieter, invisible, yet far more powerful, reached Earth. Deep beneath mountains and across deserts, vast detectors designed to listen for tremors in the fabric of space-time itself registered a new kind of cosmic heartbeat. 4 gravitational wave observatories, the twin LIGO detectors in the United States, the Virgo instrument in Europe, and the newly completed Kagra Observatory in Japan, all recorded the same signal. A short, violent ripple lasting barely a fraction of a second, but carrying the energy of multiple suns annihilated at once. The data was unlike anything seen before. It bore the signature of 2 massive black holes colliding, as had been observed many times since the first detection in 2015, but this signal contained subtle irregularities, patterns within the waveform that hinted at something more complex. The spins of the merging black holes, their rotational orientations, were misaligned, not only with each other, but also with their orbital plane. Theoretical models suggested that such a configuration could not easily arise from the simple collapse of 2 massive stars in a binary system. Instead, these black holes appeared to be descendants, the products of earlier mergers, themselves born when 2 smaller black holes combined in ancient cosmic cataclysms. In other words, the detectors had captured evidence of second-generation black holes. Their parent systems had already lived, died, and merged long ago, releasing earlier bursts of gravitational radiation that might have reached Earth millennia before the invention of modern science. These new, heavier black holes then found each other within dense stellar clusters, perhaps in the hearts of young galaxies or globular swarms, and repeated the dance of creation through destruction. When they finally collided, the universe trembled again, and we, fragile creatures orbiting a yellow star, heard the echo. The implications were profound. For the first time, scientists could trace the genealogy of gravity itself, a cosmic family tree written in waves of space-time. Each generation of black holes grows more massive, more energetic, reshaping the dynamics of galaxies. Their mergers seed the centers of future galaxies, eventually giving rise to the supermassive black holes that anchor cosmic structures. What had once seemed like distant, isolated phenomena were now understood as links in an evolutionary chain. The birth, growth, and reproduction of the most extreme entities in existence. The global network of observatories worked tirelessly for months to decode the signal. Using supercomputers, physicists compared the observed waveform to millions of theoretical templates generated by Einstein's field equations. The result was clear. The source lay billions of light-years away, yet its fingerprint was unmistakable. A merger of two black holes, each around 50 solar masses, spinning in misaligned directions. Their union produced a single black hole of roughly 90 solar masses, radiating a surge of gravitational energy equivalent to 3 suns converted entirely into motion. This discovery marked a turning point in astrophysics. Until now, gravitational wave astronomy had been about detection, proving that such waves exist, confirming Einstein's century-old prediction. But now it became a tool of exploration, capable of reconstructing histories, revealing environments, and even suggesting where and how these monstrous objects are born. For the first time, we could listen to the universe not only as it is, but as it was, its echoes traveling across eons, carrying tales of cosmic ancestry. And so, within a span of months, humanity encountered 3 profound mysteries. The meteor blazing above a sleeping city, a wanderer from beyond the stars defying solar winds, and the deep murmur of space-time unveiling a new kind of black hole. Each discovery, distinct yet connected, expanded the map of what we know and what we dare to imagine. They reminded us that our planet, small and fragile, is immersed in a vast conversation of forces and events that began long before we existed and will continue long after we are gone. Science does not end with answers. It begins with them. The Moscow bolide became a story of curiosity and persistence, Triatlas, a symbol of the universe's boundless diversity, and the black holes, a revelation that even within darkness there are generations, evolution, and legacy. Together, they show that discovery is not a single event, but a rhythm, a continual pulse of wonder that moves through human thought as surely as gravitational waves move through the fabric of reality. And as those waves fade into silence, the next questions rise. How many other travelers are approaching unseen? And how many more hidden collisions shape the cosmos we call home? When scientists speak of discoveries, they often mention instruments and data, but rarely the quiet persistence that lies behind them. The patience of minds that have stared for decades into numbers, searching for whispers of meaning. Behind every flash in the sky, every faint signal in a detector, stand people whose names may never be known to the public, yet whose eyes have seen farther than most will ever dream. The story of these recent cosmic revelations is, above all, the story of human wonder, a bridge between intellect and imagination. Consider first the luminous visitor that cut across Moscow's dawn. It was gone in seconds, but those few seconds condensed years of training, instinct, and curiosity. Among those who analyzed the event was Stanislav Korotky, a veteran observer of the night sky and one of the most respected amateur astronomers in Eastern Europe. He is called an amateur only because his passion began outside the walls of academia, yet few professionals could match his sharpness in decoding celestial trajectories. He gathered videos from cities and villages, stabilized them frame by frame, found the faint traces of stars invisible to untrained eyes, and from those points reconstructed the path of the mysterious bolide. It was a patient, almost monastic process, aligning seconds of footage, comparing brightness gradients, correcting for lens distortions. His conclusion that the object was natural, not artificial, reminded the world that true discovery often lies at the intersection of science and devotion. Such dedication mirrors that of the observers who watch the deep sky each night from the high deserts of Chile. In a dome surrounded by silence, the Atlas telescope turns its gaze across millions of stars, searching for changes too small for human eyes to notice. It was there that Triatlas revealed itself, a pale wanderer among constellations. The telescope's operators, engineers, and software designers together form a hidden orchestra, each note of which contributes to the grand symphony of data. They do not simply photograph the sky. They measure the pulse of creation itself. For months, they followed Triatlas as it drifted sunward, tracking every spectral shift, every glimmer of sublimating ice. What fascinated them most was not just the physics of the anti-tail, but the poetry of its existence. Imagine a body born in the freezing outskirts of another star system, carrying within it a chemistry foreign to our sun. For countless millennia it floated through the interstellar void, untouched by light, until by pure chance it crossed the thin spiral arm that shelters our world. For the first time, sunlight brushed its surface, warmth touching ancient frost, and in that instant gases erupted like breath after endless sleep. The anti-tail was not an act of defiance. It was the awakening of memory. Each grain of dust carried the signature of the place where it was born, perhaps in a disk around a dim red star, or in the shattered debris of a supernova that seeded new worlds. To study it was to look through time, to glimpse what other solar systems might be made of, to imagine what stories their comets might tell if they too visited strangers' skies. And then there are the guardians of the invisible, the physicists who listen not to light but to the trembling of space-time. In underground caverns and remote plains, they built instruments of almost sacred precision. Each detector, such as the Kagra Observatory, deep beneath Japan's mountains, rests within a chamber colder than outer space, where mirrors hang from threads thinner than a human hair. Through these mirrors pass laser beams, their paths so stable that the smallest distortion, a movement smaller than 1,000th of a proton's width, can reveal the passing of a gravitational wave. When the signal of the second-generation black holes arrived, it was these mirrors that first felt the universe's heartbeat. Behind that vibration lay the labor of decades. Engineers polished the mirrors until they were smoother than any surface found in nature. Cryogenic systems cooled them to near absolute zero, silencing even the restless jitter of atoms. Mathematicians created algorithms capable of recognizing patterns buried in noise, transforming chaotic oscillations into symphonies of meaning. And when the data emerged, the unmistakable curve of a double merger, the entire global network of scientists knew they were witnessing a moment when theory became memory. What makes the discovery of second-generation black holes so moving is not only its scientific weight, but its philosophical resonance. In their collisions, we see the cycle of creation and renewal that mirrors life itself. Each generation of black holes is born from the death of others, inheriting their mass, their spin, their momentum, a continuity of being written in the geometry of space-time. In a sense, they are cosmic descendants, bound by lineage though separated by epochs. The universe, through them, rehearses its own immortality. These new findings have also reshaped our plans for the future. The expansion of gravitational wave observatories across the globe will soon allow scientists to triangulate the sources of such signals with unprecedented accuracy, enabling optical telescopes to seek their electromagnetic counterparts in real time. Perhaps the next detection will coincide with a visible flash, a brief luminous outburst marking the birth of another black hole. When that happens, humanity will, for the first time, watch and listen simultaneously to the same cosmic event, perceiving the universe through both its light and its gravity. As for Triatlas, it will soon vanish forever, flung back into interstellar darkness by the gravity of the sun. But before it fades, observatories will continue to gather data from its spectral tail, cataloging every molecule and grain of dust it sheds. Those measurements will help define what kinds of matter exist in the frozen reaches between the stars, how such bodies form, and perhaps how life's essential chemistry is scattered through the galaxy. In the quiet months after its departure, scientists will sift through terabytes of data, seeking patterns invisible to the naked eye. Somewhere in those patterns may lie hints of other interstellar travelers already approaching. Silent voyagers that will, one day, announce themselves with a faint point of light moving against the fixed stars. Even the Moscow bolide, brief as its existence was, leaves an enduring trace in the collective pursuit of knowledge. Expeditions will continue into forests and fields, guided by satellites and magnetometers, hoping to find a fragment that once blazed across the sky. If such a piece is ever found, it will likely rest within a museum's glass case. A small, dark stone, unremarkable to anyone who does not know that it once burned like a second sun. Yet for scientists, it will be a reminder that even the most ordinary rock can hold the history of worlds that no longer exist. All these stories converge upon a single theme: humanity's unending dialogue with the cosmos. We are no longer passive observers looking upward in wonder. We are participants in a conversation that spans billions of years and uncountable distances. Every telescope, every detector, every expedition is a word spoken in that dialogue, a question asked in the universal language of curiosity. We send machines to orbit, probes to other planets, radio waves into the stars, and the universe replies in flashes, in waves, in whispers of gravity. It is humbling to realize how much remains unseen, somewhere beyond the reach of our instruments. Perhaps black holes of even higher generations collide, producing ripples that will one day pass through our detectors. Perhaps more interstellar bodies like Triatlas are already en route, carrying in their icy hearts the chemistry of forgotten stars. Perhaps right now, above another city, another bolide is crossing the sky, witnessed by eyes that will wonder just as we did. The cosmos does not rush. It unfolds in cycles far longer than human lifetimes, yet it allows us brief moments of revelation, glimpses through the curtain of infinity. Those moments are enough to remind us why science matters, because to explore the universe is to understand ourselves. The elements that compose our blood once burned in stars. The iron in our veins once lay within the core of a supernova, and the water that sustains us may have arrived aboard ancient comets, much like Triatlas. So when we speak of meteors, interstellar travelers, and black holes, we are not describing distant phenomena. We are describing parts of our own origin story. The falling light above Moscow, the icy wanderer from beyond the sun, the merger of black holes billions of light years away. They are all echoes of the same cosmic process that gave birth to everything we know. We are not separate from the universe. We are its continuation, its awareness made flesh. And thus the story closes not with an ending, but with an opening. The next bolide will appear. The next interstellar comet will be found. The next gravitational wave will arrive, and again we will listen, measure, and marvel. For as long as there are those who look up, the universe will never fall silent. It will keep speaking through light, through motion, through the invisible music of space-time. And we, fragile yet persistent, will keep answering, forever trying to understand what it is saying.